Hey guys, so today I'm going to introduce to you one new idea, and then we're going to continue exploring this idea of circular motion. We started it with Super Monkey and the turning car in our previous video. In class, we started looking at some theme park rides that have some circles going on there, right? And so today we're going to look at a couple of different examples. The first thing I want to look at with you, though, is this one, okay? This is what is known as Newton's law of gravitation, or sometimes Newton's universal law of gravitation. Okay, from what we know, all objects that have mass exert a gravitational force on all other objects. And we've talked about that before in conjunction with Newton's third law, right? We made the comment many moons ago that as Earth exerts a gravitational force down on me, I must be exerting gravitational force up on the Earth. Same force, opposite direction, right? So we've talked about that idea in conjunction with Newton's third law. Well, this is the equation that actually allows us to calculate the force between any two objects. Up until now, we've always just used the force of gravity equals mg, but that only allows us to find the force of gravity between us and the Earth when we are on the surface of Earth. It won't actually work for any other objects, nor does it work once we leave the surface of Earth, when we're up where a satellite would be, or the moon would be, or if we're on a different planet. We can no longer use mg unless we have different values of g for all of those situations. So what we have here is a new equation that says that the force of gravity between any two objects is equal to the universal gravitation constant g, which, by the way, is 6.67 times 10 to the negative 11th. Messy units, don't worry about it. Notice that they're in SI. That's important. Times the mass of one object times the mass of the second object divided by r, which is the distance between their centers, squared. Okay, now notice also that it doesn't matter which mass you put in for mass 1 and which mass you put in for mass 2. 3 times 4 is the same thing as 4 times 3. So that connects with what we've talked about before, is that the force between any two objects must be equal, just in opposite directions. And so it doesn't matter what order you put them in. Now, it does matter in some situations what you're identifying as object 1 and object 2, because we may end up canceling some masses out somewhere down the line. And I may show you that in a little bit here. Okay, so this equation can be used to find the force of gravity between any two objects. Now, you may recognize that this g is 6.67 times 10 to the negative 11th. So that's 0.0000, right? You got to have a whole bunch of zeros before you finally get to that 667. What that means is that if your masses are small, like the force of gravity between me and you, our masses are relatively small. When we multiply that by 0.0000 all the way down to the 667, it's basically going to be 0, especially once we divide by the distance between us, which is in meters, which right now could be a number of kilometers, and therefore the force of gravity between us is very, very small, basically negligible, especially when we compare it to the force of gravity between us and the Earth. The Earth has a very large mass, and so when we multiply it, it does end up balancing out that to the negative 11th a little bit, okay? So just kind of some things to think about, recognizing how this connects to a bunch of the other things that we've done previously, because those connections, like I've said since the beginning of the year, the connections really are the important part of this course and being able to put those ideas together. All right, now with that, I would like for us to apply that to a circular motion scenario. Okay, the one that I've chosen is between the Earth and the moon. Now, some of you may be saying, yeah, but Mr. Bauer, the moon doesn't go in a perfect circle. Yeah, get over it, okay? We're going to pretend, some of you may not have known that. Yes, the moon does not go in a perfect circle around the Earth. In fact, the Earth doesn't actually stay in the very center. It actually wiggles back and forth a little bit as the moon's pulling on it, right? Because there's a gravitational force of the moon on the Earth. But we're going to assume, for the moment, to simplify it and try to understand these principles, we're going to assume that the Earth is at the center and that the radius of the orbit is constant. That's why we use an r here. It's not the radius of the planet or the radius of the moon, it's the radius of the orbit. And it's always the distance from the center to the center. It's not from surface to surface, it's always from center to center. So let's go ahead and look at this. We have a planet here, the moon, which is going around the Earth. It is going in circular motion. Now, the first thing I would like for us to do is see if we can figure out how fast the Earth is moving. Sorry, not the Earth. How fast the moon is moving. All right. Now, what we're looking at here is our speed equals distance over time. And hopefully you're recognizing that this is in some ways similar to some of those other circular motion questions that we've done so far, right? But we're doing speed equals distance over time. So we need to find the distance that the moon travels as it goes all the way around the Earth. Now, we do know that the distance, the radius of our circle is 400,000 kilometers. Now, we do need to turn that into meters. There's 1,000 meters in a kilometer, so we punch that into our calculator. And we're going to get that the distance here will be 400 million meters. So now we're going to find the distance around the circle, which you know to calculate the circumference of a circle, it's going to be 2 pi r. So the circumference, the distance around the circle will be 2 times pi times our radius, which we just said was 400 million meters. And we always put everything in meters and seconds because that's what we're going to need in order to make sure that our units always end up being okay. Then we'll put time on the bottom. Now, you may or may not know that it takes the moon approximately 28 days to go all the way around the Earth. That's why a month is 28 days. A month, according to the moon, is 20. That's why some faiths, some areas of the world use what's called the lunar calendar. For them, a month is actually 28 days. They don't do this stuff with sometimes it's 30, sometimes it's 31, sometimes it's 28 or 29, depends on the year. They just do 28-day months. All right. If we take 28 days, and I know that there are 24 hours in a day, I can do 28 times 24, and that'll give me 672 hours in a month. There are 60 minutes in an hour, so I can multiply that by 60, and I get about 40,000 minutes in a month. And then I'm going to multiply that by 60 again because there are 60 seconds in a minute. And so I get up to 2419200, and that is in seconds. Just like this is in meters, remember we want everything to be in those base SI units. Okay, so we should now be able to do the math here. We're going to go 2 times pi, which I know I have a pi button on here somewhere. 2 times pi times 400 million, and then divide by 2419200, and we get that the moon is moving at approximately 1,039, about 1,040 meters per second. I'd be fine if you put 1,040. That would be 3 significant figures. Please don't write out like 5 decimal places. It's not exactly 400,000 kilometers. That's already rounded. So if you put a whole bunch of decimal places, that's not meaningful at all. So be reasonable. If you want to put 1,039, that's fine. Okay, so we've got the speed of it now. Now, you know, we're talking about circular motion as part of our exploration of theme park physics. And in circular motion, in order for an object to move in a circle, there must be a centripetal force. There must be a force that is in that radial direction that is causing the object to go in a circle. Otherwise, the object would just go in a straight line. So the question for you is, what is the centripetal force? Now, hopefully, you're recognizing that the centripetal force is the force of gravity, right? It's the force of gravity between the Earth and the moon that's causing that inward force. That force is always straight towards the middle. The centripetal force is always straight towards the middle, all right? And so that inward force is what makes sure that the moon doesn't go in a straight line. It keeps bending a little bit towards the Earth. And it's at just the right speed, at just the right location, that it's able then to continue in that circle going around and around and around the Earth. All right, so the centripetal force is the force of gravity between the Earth and the Moon. All right, now our next task is I would like for us to actually calculate the centripetal force. All right, now in order to be able to do that, I'm going to have to give you one piece of information. We need to know the mass of the Moon. The mass of the Moon is about 7.3 times 10 to the 22nd kilograms. So mass of the Moon is 7.3 times 10 to the 22nd kilograms. And so we will use that. Remember, the centripetal force we learned in our past video and in class today is mv squared over r. We'll use the mass of the Moon. The centripetal force will always use the mass of the object that's going in the circle because it's the force required for that object to go in a circle. So we'll have that 7.3 times 10 to the 22nd. It is in kilograms. That's our SI unit. Times our speed squared, which was that 1039, which we did do meters and seconds. That's why it was so important that we don't use months for our time and we don't use kilometers for our distance. We want everything in SI so that everything just matches up here. And then we're going to divide by the distance or the radius of the circle through which the path is, and that again will be that 400 million meters. And now we should just be able to throw those numbers into our fancy calculators here. So we go 7.3 times 10 to the 22nd times 1039 squared, and then divided by 400 million. And I end up getting that the required centripetal force is 1.97 times 10 to the 20th. Force is in newtons. So a rather large force, but that's okay. The Earth is large, the Moon is large. Therefore, I end up getting a large force for my centripetal force. Okay. Now, the last thing I would like for us to do with this Moon-Earth system is we now actually have enough information between our centripetal force and our Newton's law of gravitation. It had to come in here somewhere, right? We now have enough information that we can actually calculate the mass of the Earth based off of all the other knowledge that we have. Okay? Because we have said that the centripetal force is the force of gravity. If that's the case, then the force of gravity must be 1.97 times 10 to the 20th newtons. All right, so we're going to use that in this equation. So we're going to come over here. We'll say, okay, so the force of gravity, which is the centripetal force, so 1.97 times 10 to the 27th, okay, 1.97 times 10 to the 20th, equals G, which is 6.67 times 10 to the negative 11th, times m1, which I'll go ahead and use the mass of the Moon, which was that 7.3 times 10 to the 22nd, times mass 2. Mass 2 is the mass of the Earth. That's hopefully what I'm going to be able to find. All divided by the distance squared, which still is that 400 million meters. All right, so from there we should be able to do the math. We'll take that 1.97 times 10 to the 20th. We're going to get this off of the bottom, so we're going to multiply by that 400 million squared. This is going to give us a really big number. I've got 3.15 times 10 to the 37th. Then, once this is over on this side, I need to divide by this, and I need to divide by this. Now, if in your calculator you're writing 6.67 times 10 to the negative 11th, you need to make sure that you put that in parentheses when you divide it. Okay? I'll show you on my calculator. Right now, you can see this is the number that I have Sorry, it's not very clear, but you get the idea. Okay, so that's the number I have. So when I do divided by, I'm going to put it in parentheses, 6.67 times 10 to the negative 11th power. All right. So you see here that I put my 6.67 times 10 to the negative 11th in parentheses. That makes sure that it keeps all of that together. If you don't do that, then it's going to divide by the 6.67, and then it's going to multiply by the 10 to the negative 11th. Now, many of your calculators have an EXP or an EE. If you use that, then it actually solves the problem. You don't have to use parentheses. But if you don't know what I'm talking about, don't worry about it. Just make sure that you put the 6.67 times 10 to the negative 11th in parentheses. Okay? And then we will divide by that 7.3 times 10 to the 22nd. Again, put that in parentheses if necessary. And I get approximately that the mass of the Earth is 6.47 times 10 to the 24th. Now, is that reasonable? Well, remember the mass of the moon was 7.3 times 10 to the 22nd. This is 6.47 times 10 to the 24th, so I've got 2 extra 10s there. 10 times 10 is 100. So what I ended up with is that the mass of the Earth is about 100 times bigger than the mass of the moon. I'm okay with that. That seems acceptable to me. That's within the realm of reason, right? If I got something like twice as big, that's a problem. Or if I got something where it said the Earth is 1,000,000 times bigger or only half as big, those would be problems. But 100 times bigger, that seems reasonable to me. I know it's bigger, it's significantly bigger, but it's not like Earth and then thimble point moon, right? So anyway, here we go. Reasonable answer. All right, so hopefully that's helpful in helping you see how we can kind of use this Newton's law of gravitation in connection with the centripetal force and that circular motion that we've kind of been exploring a little bit with our theme parks. Okay, so give me just a second. I'm going to erase this because we got one more thing I'm going to have you look at before we finish this video. All right, so I got with me today Mr. Pig. I know, you're thinking, Bdubs, you are so creative with your naming of animals, because I had Mr. Monkey last time, I got Mr. Pig this time. Hey, it's not my fault I don't have time to come up with fancy names for my animals. You come up with a name. All right, here we go. So Mr. Pig here is actually a pretty fancy pig, because just like Mr. Monkey, he can fly. So here we go. Give him a second. Takes him a minute. And look at that. He is flying in a nice, lovely circle right there. And he is actually a little bit close to the board, so he does run into the board eventually. But you can tell that he's moving in a fairly nice circle there. Now, a couple of the other things you might notice is that there is a string. If you didn't see the string, he's not really flying. He's attached to the string. Okay, but the string is kind of over at an angle like this, and he is then coming around kind of like this, right? And the string is always going to be attached kind of to the center of the ceiling there, and it's going around that point there. All right. Now, hopefully what you noticed is that the pig does go in a fairly decent circle. So he's going in circular motion. Now, if there is circular motion, there must be a centripetal force. Now, remember, centripetal force is not magic. It has to be one of the forces that we've previously talked about. So let's do this. Free body diagram. Sometimes it's helpful, a lot of times it's helpful to draw a free body diagram. So here's my pig. Here's the string. Okay, I want to be careful because the string itself is not a force. The string is just the string. But I'm going to use that just so I can visualize it. And then the pig is kind of going back into the back like that, and then it comes forward like that. And so this is kind of my, I'm looking at it maybe from this perspective right here, right, where you can see the angle of the string. The pig's going to come this way, so kind of out of the page, and then it comes back into the page there, and then out again. That's what I'm trying to draw here, so I'm not a very good 3D artist. Obviously, all my objects are squares. That's what happens when you become a physics teacher. But you get the idea. It's going in a circle. Here is the center of the circle. So according to everything that we've talked about so far, the centripetal force must point towards the center. All other forces have to balance out. If the other forces don't balance out, then it ain't going in uniform circular motion. It's not going to go in a constant speed circle. So, what is the centripetal force here? Well, what are the forces on the pig? We've got gravity pulling down, and then you've got tension pulling up in the direction of the string. Now, what you may notice is that the tension has, and you remember we talked about this last semester, the tension has two components. It has a vertical component, and it has a horizontal component. Okay? Now, some students like to label those. They like to say, okay, so this is the Tx, that's the tension in the x direction, the horizontal tension, and this is Ty. And I know you may be saying, but those aren't different. They're the same. They're all there. Yeah, they are all there. They're all the same. And that, you know what, it's okay. If we can separate it in our brain, then it actually makes the physics easier. Okay? So you've got a vertical Ty and a horizontal Tx that when you add those together, they give us this tension going that way. Okay? Now, that having been said, the pig, as it goes around that circle, is not accelerating up and down. Now, what that means, according to Newton's first law, it's going to maintain its vertical motion, which is not going up or down at all, if the forces are balanced. And so, therefore, we know that the vertical tension and the vertical force of gravity must be equal. Okay? Now, what's remaining then is the unbalanced horizontal component of the tension. And so we have here a horizontal component. This is that vector right there. That is the horizontal component of the tension. It's not a different force. It's not a new force. It's just a part of that tension force that is pointing towards the middle. And so therefore, our centripetal force is the horizontal component of the tension. So this goes back to what I said at the very beginning about centripetal force, is that centripetal force can be one of the forces. It can be the sum of the forces. Sometimes you'll have different forces that are working together to create this centripetal force, or it's also possible that it is just a part or a component of one of those forces, and that's what it is in this case. Now, I would like to pose a question to you. I would like for you to think about, what information do we need? What data do I need to gather in order to be able to determine the amount of centripetal force required to make the pig go in a circle? So thinking about what's happening here, what data would I need to gather? What information do I need in order to be able to calculate the centripetal force, assuming that he doesn't run into the board? Sorry, I got him a little bit close. I made my string a little bit too long for this. Okay? So think about that. I would like for you to actually pause the video for just a couple of minutes. Write down your thoughts. I'm going to give you the answer in a second, I promise, but I want you to try it first. Think about, what information do you need to measure, and how would you gather it to figure out what the centripetal force is? What's the value of the centripetal force for the pig going in the circle? Okay? So, pause now. Really, pause now. Okay, so hopefully you've now had a chance to think through it, and my hopes are that what you did is you said, well, in order to calculate the centripetal force, I need mv squared over r. So, what do I need to measure? I need to measure the mass of the pig. Now, that I can measure using a balance, or one of the scales, the electronic scales. I can use that, or maybe even one of the spring scales if you want to use one of those, but we can measure the mass of the pig. Okay? The next easiest one, I'm going to come back to the speed in just a minute, but the next easiest one, of course, is r, which is the radius of the circle. And so we would need to measure the radius of the path. And there's a number of different ways you can do this. Probably the easiest way is just to have a partner stand here, and as the pig comes around, catch the pig on this side and then allow the pig to mark that position, and then allow the pig to go around, and then have him mark it on the other side, measure that distance, which will be your diameter, and divide by 2 to get the middle. I've seen students do a bunch of other things. I've seen students try to create a video and measure the circumference. I've seen students that do things like, well, I'm going to just hold the meter stick in the middle and I'm going to see where it passes over my meter stick. You can do that as well. But you have a variety of different ways. Some are better than others, but you have a variety of different ways that you could use to estimate the radius of the circle that the pig is traveling. I find that diameters are easier than radii, but you know, it's up to you if you were to do a lab like this. Okay, so you've got the radius of the path. Last of all, we do need the speed. Now, we've done quite a bit of this, so I'm hoping that by now you have an idea of how you would calculate that speed. Remember, speed is distance over time, so you need the distance around the circle, which you just calculated the radius, so you can do your 2 pi r to get the distance around the circle, okay? And then we need the time. We need the time, which you should be able to measure using a stopwatch. Now, the best way to do it is to time and measure 3, 4, or 5 circles and stop and then divide by how many there are. It reduces uncertainty if you do that. But, of course, if you're not worried about error and uncertainty, you just start it and stop it when it gets back around. So there's multiple ways to do that. However, we do need, for this, the speed. We need distance. We need time. Distance we get from 2 pi r, from the radius that we already measured. Time, you'll have to use a stopwatch to measure the time of going once around, to measure the period, right? Okay, so that's actually it. I just wanted you to kind of think through that, think through some different situations where we have some circular motion. In class, we are focusing on the theme parks, but I wanted you to see some different situations where circular motion applies, especially this one, because, sorry, not this one, the one that was up here earlier, the one about the moon going around the Earth, because we are going to do an astrophysics unit later this year, and I want that already present in your mind, and how does the physics that we're learning now apply to the things that we're going to learn later. Okay, so that's it for today. Thanks for hanging out. I'll see you in class.